Alright, hello everybody. So by now you should have this drilled down. You should be in your seats and starting your do now. Go ahead, we're only going to take 3 minutes. Take 3 minutes to get through as much of this do now as you can, silent and solo. You can go ahead and begin if you haven't already. You can pause the video here. Alright, so coming back to this do now. For number 1, we're being told, hey, we have this function here where k of x is equal to 3x squared minus 4x, and we need to evaluate each of the following. So I have k of 2 and k of negative 1. Now, really quick looking at these, I can see right away that luckily we're given inputs. So we're given inputs, and remember from yesterday from our notes, whenever we're given inputs, we simply take that input and substitute it in for every x in our problem. So we're going to go ahead and do that. So for k of 2, we're going to have 3 times 2 squared minus 4 times 2. Now, make sure that we're doing our squared first. Remember that this is going to be 2 times 2, which is going to give us 4. So we're going to have 3 times 4 minus, and I'm going to go ahead and multiply these two together. 4 times 2 is going to be 8. So I'm going to have 3 times 4, which is going to give me 12, minus 8. So I know that the k of 2 is going to give me 4. And I'm going to do the same thing over here for b, just with negative 1 instead of 2. So the k of negative 1 is going to be equal to 3 times negative 1 squared minus 4 times a negative 1. Negative 1 squared is going to give me a positive 1. So it's really going to be 3 times positive 1, because remember, a negative times a negative is going to be a positive. And then we're going to have minus 4 times a negative 1. Well, 4 times a negative 1 is going to be negative 4. So I'm going to have minus a negative 4 over here. So I know 3 times 1, that's just 3. But when we're subtracting a negative, we're actually adding. So I'm going to have that 3 plus 4. So I'm going to find that k of negative 1 is going to be equal to 7. All right, and next we're just going to quickly take a look at number 2. Number 2, as you can see, says just think about it. So a discount ticket company sells tickets to Broadway shows. Currently, they're selling tickets to Wicked at a discounted rate. In order to purchase tickets, there is a service charge of $8, and each ticket costs $5. What a steal! The function s of t is equal to 5t plus 8. Can be used to determine the total cost of t tickets. And so what we're thinking about, and the answer, or the question that we're hopefully trying to approach here, is which of the following graphs is a better representation for the function s of t, and explain how you came to your conclusion. Now, looking at these, if I'm buying tickets, right, it's important to think about real world tangible things. And so if I'm buying tickets, what I'm really looking at in these two graphs here, notice that we have this portion that's missing in this graph over here, right? There's nothing there. And so the real question is, does it make sense to actually have this line? Well, for that, we have to look at what this line actually represents, right? This lovely line starts at 0 and goes to the left. So notice that the part that's missing is everything to the left of my y-axis, or all of my negative x values. So what this really comes down to is, does it make sense to have negative x values or not? That's really what we want to ask. And so in order to actually answer that, we look back at the problem. And so when we're looking at this, I know I've been saying x values, it's really t values, and when we look at tickets, it's important to know that we can't buy a negative number of tickets. That doesn't make sense, right? Because really you'd be selling tickets, and you're not going to sell tickets on a website that's selling tickets. So for that reason, we're going to say that B is a better representation, because we can't buy negative tickets. And so that is going to bring us into our notes. Take 30 seconds, copy this down if you need to. Go ahead and pause the video if you need to, but then we're going to move on. All right. So go ahead and turn to your notes. We have two vocabulary words. We're going to be looking at domain and range today. Now, domain and range are two very important things that we have to know about when looking at a graph. First up, we're going to look at domain. Now, our domain is the set of all possible values for the input, otherwise known as our x values, or in our last question on our do now, it was our t values. So our domain is a set of all possible values for the input. And the range is simply the set of all possible values for the output. So again, domain is going to be our input, our range is our output. If we want to think about it x and y values, you can go ahead and do that. It might change in the context of your problem, but your domain will always be your input and your range will always be your output. And so what this is really getting at, and the heart of the question that we're trying to look at today, is what are all possible values for x and y when looking at a set of data? It could be a graph, it could be a function, it could be set notation like we're about to see in example 1. But that's what we're trying to answer, is what are all possible values for x and y? Go ahead and pause the video if you need to. Make sure that you have these down, and make sure you have this key question down, because that's really going to be what we're addressing today. All right. So in example 1, we're being asked, what is the domain and range of the relation below? So this down here, the way this is written, this is called set notation. You can go ahead and just make that note. We'll see it a few more times. It's not something that you need to be overtly familiar with, but it's good to know what this is. It's set notation. And so, what is the domain and range of the relation below? Well, the domain, I know, are my input or my x values. So I'm going to take a look at what I've got going on here. And I know that for this domain, I have, and again, I'm still going to use that set notation. I have 2, 3, 4, 5, and 6. Right? Because those are all my x values. And for my range, I just take my y values. It's that simple. I'm actually going to circle these. Ooh. So it's a little bit easier to see and I'm not causing too much clutter. So for my range, I'm going to have, and I'm going to do these numerically so that I have my lowest on my left and I count up. So I'm going to have 0, 1, 2, and 3. Now notice in our range, we actually use 1 twice, right? We have it right here and right here. It's not important, or not necessary rather, for us to rewrite this more than once. We know that, hey, if 1 is in our range, then 1 is a possible outcome. So that's really what these are saying. What are the possible values? Well, 1 is a possible value. It just happens to show up twice. So now we're going to jump down to example 2. Now, example 2 says that given the graph of f of x equals 3x plus 4, identify the domain and range. So we have something a little different, right? We don't just have, this like set of numbers or the set of coordinate points. And so how we actually write this is going to look slightly different because we don't have exact values. And so looking at our domain here, when looking at what makes up a domain and a range, we're really trying to figure out, are there any restrictions going on in our graph? And we'll kind of get more into that. But that's what we want to see. And so as you can see, we have this lovely line, right? There's not arrows on this, but we're going to assume that there should be, and that this line does in fact continue on forever. And so because of that, I know, hey, this line is going to go on forever, which means that this line is eventually going to hit every single value. And so we have a few different ways that we can write that. I could say, hey, I know this is going to be all real numbers. I could say that I know this is going to be negative infinity is less than or equal to x, which is less than, or sorry, this should just be less than. You cannot equal infinity. That is my apologies. So negative infinity is less than x, which is less than positive infinity, right? Because this says, hey, it's going to go on forever. That's what this is saying. Or the other way that we can write this actually comes from this right here, is this real numbers. This has a special notation and a special symbol. And I apologize as I am not going to do it justice, and whoever's there can hopefully draw this better on the board if this doesn't come out well. But we call all real numbers, or we notate it with this lovely R like this, with a line through it. This is how we say all real numbers. And so looking now at my range, now that I have my domain, I can see, hey, there's also no restrictions on my y-axis, right? Because domain is going to be that x-axis. Is there any issues going left to right? Well, no, there weren't. Now I'm looking, are there any issues going up and down on my y-axis? Well, no, because again, this line continues forever. And so it's going to be a similar thing. In fact, it's going to be the exact same thing. So I know that my range is all real numbers. I'm actually going to move this because it's going to pop up some text. So there we are. So again, my range is all real numbers. And so now we have some lovely key takeaways. Before we get into the takeaways, I know one has already popped up, but take 30 seconds, pause the video if you need, copy down what we have here, for example, 1 and 2, and then we'll move on to our key takeaways. All right, so moving to our key takeaways, we have, I believe, 2 of them really that we want to highlight and make sure that we're stamping. The first one is, sometimes a relation has all possible values of x and or y represented. In this case, we say the domain and range, domain or range is all real numbers, right? Which is exactly what we saw here. We said that this would be all real numbers, or represented by this lovely R with a line through it. If it's not all real numbers, though, we say that the domain or the range is considered to be restricted. Right? This is our lovely little vocab word, restricted. And again, that's really what we're looking at. Are there restrictions? Are there any issues that we're going to have when looking at this graph that are going to cause it to not be able to encompass all values or certain values? So go ahead and pause the video if you need. Make sure you have these key takeaways down. And then as soon as you do, we'll move on. You can go ahead and pause it. All right, so we're going to move into problem set A. So problem set A, we're just going to focus on these first 3 questions here. We just want to focus on these first 3. 1, 2, and 3. You're going to have about 7 minutes, 6.5, 7 minutes to work on these 3 questions. Go ahead and work silent and solo, and you can begin. You can pause the video here. All right, so we're actually going to go over all 3 of these questions, because on some of these it's like really quick, which is awesome. For number 1, looking for the domain and the range, again, I'm looking to see are there any issues or any restrictions we're going to have on our x-axis, so across left to right, and no, right? Because we see that this has arrows on it, and we see that the function is y is equal to x plus 2. Now there's no restrictions there for y equals x plus 2. That x can be any number at all, right? There's nothing saying it can't be anything. And so in that case, we know that the domain is, just like we saw in our notes, going to be all real numbers. And for our range, once again, going up and down, or even looking at our equation, we know there's no restrictions for y. Y is going to end up hitting every single value. And so because of that, hey, you know what? Our range is also going to be all real numbers, just like it was up above. And so again, this comes from the fact that there are no restrictions. And so looking at 2, now number 2 is a little bit different, right? Because we have this point here. And hopefully this copied well, and I apologize if it didn't, but this point lies at -2, -3, right? That's where that is. And so I know that beyond this to the left, this line doesn't exist. There's nothing here. And again, we can assume that this is an arrow up here. So I know that, hey, starting at this point, it then continues on forever. Okay, so what that really means is that for our domain, well, our domain is going to be where x is greater than or equal to -2. Because again, it obviously can be -2 because I have it right there. In our range, our output or our y value is going to start at -3. So it's going to be really similar, but it's going to be that y has to be greater than or equal to -3, right? Because I have everything above that, and I have everything to the right of that. I just can't go down past this point. So this is my starting point, quite literally. So again, our domain for 2 is going to be that x is greater than or equal to -2, and our range is going to be that y is greater than or equal to -3. And so looking at number 3, we're being asked, what is the domain of the relation shown below? Now, important to note, we're only being asked about our domain here. And so because of that, we're only going to look at our lovely x values for these coordinates. And so when we do that, I'm just going to go ahead and list out what I have. My domain, I have the 0, 1, and 4. Okay, well I know, hey, I'm going to have 0, 1, and 4. Again, just like we saw in our notes in example 1, I don't have to list these out multiple times. I can simply just put 1, 0, 1, and 4, and that's all I need. And if I look, hey, I see that, hey, this is number 1. So number 1 is going to be our answer. Now, if you had picked anything else, there's a good chance you had possibly looked at the y values and used your y values. But it's important to note that, hey, the rest of these start with -2, and notice that -2 isn't an x value. It's not an x value at all. So even if you weren't sure exactly how to write them and you had, 0, 1, 1, 4, 4, the key giveaway here is that it can't be either of these because -2 isn't an input at all. And when we look at domain, we're looking at our inputs. All right, go ahead and pause the video here if you need to. Make sure you have this all down. Hopefully you're starting to see this and this isn't being too much, but we're gonna have some more practice with it, so don't worry. Pause the video here. All right, so we're now going to move on to problem set B. For problem set B, I want you to specifically focus on 3 and 4. So start with 3 and 4. If you finish those two and you have more time, awesome. Go through the rest of it. But start with 3 and 4 and make sure you have something down for those. You'll have probably, let's say 6 minutes. 6 minutes again for 3 and 4. And again, if you finish those, move on to the rest of the problems. But again, work on these silent and solo. Go ahead and begin. You can pause the video. All right, so we're gonna take a look at 3 and 4 here. So 3 says a car travels 30 miles on a gallon of gas and has a 20-gallon gas tank. We need to let G be the number of gallons of gas the car has in its tank. And then we know that the function d of G equals 30G gives the distance D in miles that the car travels on G gallons. So we want to know what are reasonable values for the domain and what are reasonable values for the range. So right away, I am going to say, hey, for our domain, I know exactly what we work with our domain. It's our input. And if we look over here, as we talked about, this lovely variable is our input. And so our domain is going to be looking at G gallons of gas. And so looking at this problem, I see that we have a 20-gallon gas tank, right? That's important. And so if we only have a 20-gallon gas tank, then hopefully it makes sense that I can't go over 20 gallons, right? I can't put 21 gallons of gas in a car that only has a 20-gallon gas tank. I'm going to be causing some issues at the gas station if I'm trying to do that. And likewise, on the other end, so we're going to start here. We know that's going to be, if we have our x here, 20 is going to be our cap, right? We can't go over 20. So x has to be less than or equal to 20. But on our other end over here, hopefully it makes sense that just like we saw in our think about it on our do now, we can't have negative gallons of gas. That just doesn't make sense here. And so because of that, we know, hey, this has to start at 0, right? Hopefully you're not hitting 0, because then you're on E. But this can't go any farther than 0. We can't put -1 gallons of gas into our car. It just doesn't make sense. And so now looking at the range, now the range I know is going to be d miles. So, and we're going to actually switch this up. Apologies, this should be a g, because remember we have to use the function. We have to use the variables that we're given, and then I'm going to have my miles down here. Now, once again, it makes sense. Hey, we can't travel a negative distance. That doesn't make sense. It's not going to make sense. You can't have negative measurements. So again, we're going to start at 0. But then we come to this lovely issue of, well, what's the maximum distance that I can drive? Well, I know that we can go 30 miles on a gallon of gas, right? So I can go 30 miles on 1 gallon, and I have 20 gallons. And so really my cap is using all of my gas to go 30 miles on each gallon of gas. So I know that my maximum range is going to be 600. My maximum range is going to be 600 miles, and that's simply just taking that 20 gallons of gas, multiplying it by 30 miles per gallon to get 600 miles. And that's my upper bound here. All right, and then for number 4, we have if a tree grows 8 inches each year, and the total height of the tree is f of n, where n is the number of years, what number set would make sense for the domain and range for f of n? Explain your answer. So let's take a look at what this actually looks like, right? So this is actually saying that, hey, we have this lovely f of n function, and that's going to equal to a times n, where n is my years and a is my inches. Inches per year, specifically. That's going to be how I calculate how tall the tree is. And so looking at our range, or sorry, our domain, we're looking at our lovely inputs. Now it's important to note that this, again, here is our input. So when we're looking at this, we're not looking at a. Remember that a is just some set value. We don't know it. It could be 3, it could be 7, it could be anything. So we're just calling it a. A is never going to change. Our input is n. N is something that could change. N is time, right? That's how it's going to change. And so our domain, we're looking at time, specifically number of years. So when we're looking at time, once again, you'll find for a lot of these, when we put these in real world context, it doesn't make sense to have negative numbers, right? We can have a tree be -1, -2, or -5 years old. Doesn't make sense. And so I know that, hey, I'm once again going to start at 0 is less than or equal to n, which is less than or equal to. Well, now we need to think, is there any restriction for this? Well, no, really, because it's going to depend on how long the tree actually lives. So I actually don't have a hard, set, fast number because I don't know what a is. So because of that, my only restriction from my domain is this, right? And we're going to rewrite this so that this is a little bit neater. my domain is simply going to be that n needs to be greater than or equal to 0. And it's just simply saying, hey, you just need to pick a year that's positive. Just pick a year that's positive. And for our range, well, for my range, I know I'm looking at f of n, right? I'm looking at this as a whole, because this as a whole is our output. And so once again, it makes sense that we can't really have negatives here. We can't have a tree that's negative 2 inches tall. Once again, doesn't make sense. So when we're looking at range and we're looking at height, we're going to have a similar restriction. We're going to say, hey, because we don't know exactly how tall it's going to get, whereas with number 3, we had some pretty clear limits on exactly what we could do. With a tree growing, there's not. It's going to be dependent on a lot of things. And so for now, we're just going to simply say, hey, you know what? This function, just like our n, f of n, needs to be greater than 0. So really what we're saying here is that both of these just have to be positive. They just have to be positive. All right, go ahead and pause here if you need. Make sure you have this down. All right. So before we move down to your exit ticket, please note this right here. Now I put it in here a couple of times and it's very similar to yesterday, but you need to make sure you get that vocab and those notes into your notebook. Again, I'm going to be doing a notebook check when I am back. But other than that, go ahead and just work on these problems. It's all domain and range. It's also the stuff that we did today. Otherwise, you have until the end of class to work on your exit ticket. Once again, silent and solo. Go ahead and begin.